Theoretical physicist Janna Levin maps out the boundaries in her new book, How the Universe Got Its Spots. Taken from a series of unsent letters to her mother, the book argues that the cosmos is both edgeless and finite. Miss Levin spoke recently at the California Institute of Technology for an hour.
So one of the, I guess, great questions of our time in terms of science is the origins of the universe. Where did it all begin? How did it get started? What was there before the Big Bang? All that stuff, the nature of space and time. I do think that there is an interesting literary and cultural phenomenon that I call scientism, that the literary agent John Brockman calls the third culture. You know, C.P. Snow's two cultures, the sciences and the humanities and arts, and they don't talk to each other. There's this abyss between the two. Brockman calls the third culture this sort of new scientific culture. Books about science, books about nature, books about the world, that if you want to be considered a literate person, you want to be part of the sort of culture of letters, you really need to read science books, because that's where the action is now. And that's bridged that gap. If you want to know what's going on, you have to have read Stephen Hawking or Stephen Jay Gould or Richard Dawkins or Ed Wilson or whatever. These are the kinds of new myths for our time that tell the big story, that offer really a complete worldview, as complete as any worldview can be, satisfying to those of us who don't need the other religious-based or non-secular-based worldviews. And I think a contribution to that is this book, How the Universe Got Its Spots, which is one of the great titles you can have for, I think, a lecture and a book. Janna Levin is a cosmologist that studies this stuff, and I do think in terms of calling science a myth, I don't mean it's not true. I mean myth as in it's a story. It's a great story. But it's a lot more interesting story than most of these other mythic stories, because it's always changing. It's not just being reinterpreted based on the language, but reinterpreted based on evidence. And so nothing changes faster, it seems like, than cosmology. It's, the universe is expanding. It's going to expand and stop. No, it's not. It's going to expand forever. It's going to expand faster, slower, whatever. And it's constantly changing. And so Janna wrote this book to sort of bring to everybody, in the form of letters to her mom explaining what she does for a living, because parents like to know that. You're going to do what? And they pay for this? How are you going to make... Anyway, she is an advanced fellow in the Department of Applied Mathematics and Theoretical Physics at Cambridge University. I made the mistake of announcing we have a Brit coming to America. She's not. She's actually from Chicago, who works in Cambridge University, holds a PhD from the Massachusetts Institute of Technology, and worked previously at the Canadian Institute for Theoretical Astrophysics and at the Center for Particle Astrophysics at UC Berkeley. So please help me welcome Dr. Janna Levin.
We've been a little slow with technical things tonight, so we'll see how it goes. I could be launched to the moon myself with all this equipment on. Yeah, I didn't realize you were all skeptics. Recently, I was talking to a woman who has a psychic parrot, who I really wanted to fly to New York to talk to the psychic parrot. And she said, no, your bad energy is going to psych the bird out. And she really didn't want me coming, but she said she had to have the bird's interests at heart. But she made these great videos where she would look at magazines and the bird would guess what she was looking at. It was really But parrots, they sound exactly like their owners. So it really sounded like she was making the bird sounds. It was not very believable. Well, down to even more ethereal things, I'm going to be talking about whether the universe is infinite or finite. And this is a branch of research I was interested in for a couple of years. I can't say I worked on it forever or that I'll work on it in the future. It's something that kind of drifts in and out of my interests. And it's not a question we've answered yet. It's something that we're looking at both from particle physics, the physics of the smallest microscopic laws of the universe, and physics on the absolute largest scale. We're trying to meet in the middle and try to understand something about the entire shape of the universe we live in. So I'm going to begin somewhere. I was going to say the beginning, but of course it's never really the beginning. As Michael said, it's just a story that keeps growing and keeps evolving. So I'll begin somewhere in the middle of the story. It was really after Einstein that we started to be able to formulate this question. And everyone's heard of Einstein, but sometimes people don't really know everything that he did. They know about the theory of relativity. And one of the great things Einstein did is he said space and time are not absolute things that just exist out there in the universe. They're mutable, evolving, changing things. Now, his theory is not a complete theory. It has certain limitations. And one of the limitations is that it assumes that the universe is infinite. And I'll be talking about how we try to take one step beyond Einstein. And we try to ask the question, what if the universe were finite? How could we know this? What kind of math would we use? How would we visualize it? And most of our talk is going to be about trying to visualize it, because I think, as Michael said when we speak in Greek, I think it would be very boring if I sat here saying, G, mu, nu, mu, pod, mod, gamma, pi. So I won't be talking in the language of the mathematics. I'll be mostly visually trying to reconstruct what the world would look like. So I liken the assumption that the universe is infinite to the old assumption that European explorers had that the Earth was flat. And if you think about it, they knew it wasn't really flat. They knew that there were mountains and hills and valleys, but they kind of thought, well, the Earth can't go on forever. It can't be infinite. They didn't really think of it as being infinite. Instead, they said it must have just an ugly edge. And they imagined that if you took a boat and you left, I've forgotten where we are. Are we in California? We're in California. If you left and you traveled in the Pacific in a boat, I've been in so many places lately, and you just went in a straight line, you got off your boat, but you kept going in a straight line, you walked, you got into a car, and you never turned left, you never turned right, you never went backwards, you would eventually come back to California again. So it turns out that I have a pointer. The Earth doesn't have some ugly edge, nor is it infinite. It's actually a smooth surface. It's edgeless, it's completely finite, and even though it's finite, it has no edge. It's bounded. Bounded but edgeless. That's the trick. We want to make an entire universe in the same way. We want to say, if the universe is not infinite, does that mean you will just travel in a spaceship and eventually come to the end of space itself, where the universe just ends? And that's very ugly. We don't want to do that. That would not be a positive extension of Einstein's theory. That would be ugly. So what we try to do is we try to say, well, what if the entire cosmos was like the Earth? If it was finite, bounded, but edgeless? And what would that universe look like? It was discovered by engineers Penzias and Wilson when they were working for Bell Labs. They had this radio dish that they were, I think it was a radio dish, that they were trying to clean out to get a better telephone signal. I'm not sure how it all works, but what they discovered was the light left over from the Big Bang. They discovered the echo, that last note, that little hum, that static, that surrounds us in all directions, wherever you look, this remnant from the origin of the universe. One of the most important discoveries for cosmology of the last century, for sure. And this picture, I don't know why I made this flat. If you imagine launching a satellite into space that looks over the entire sky, it will actually make a spherical picture of the sky. So there was a satellite launch called COBE, which looked all over the entire sky for this radiation left over from the Big Bang. Now, they actually got a map of a sphere, but if you cut it open and lay it flat, it makes this kind of oval shape. This is it's just like taking a map of the Earth and flattening it out onto a flat sheet of paper. I think from now on I'm going to replot this spherically. All cosmologists look at these in these oval shapes, and now as I'm standing in front of you, I'm wondering why we do that. It's so that we can see the front and the back at the same time. That's what it is. If you have a sphere and you can only look at one side at a time, and that's a problem. So here it's projected out so we can see, just like looking at the entire surface of the Earth at once. And these are little hot and cold spots left over from the Big Bang. Little tiny temperature differences. And I liken these to, in animals, birthmarks, mammalian coat patterns. It turns out that in these hot and cold spots is going to be the secret of the shape of the universe. And there is a trend in mathematical biology where the biologists try to understand how the mammal got its spots, how the leopard got its spots. And it's realized that it's a very similar problem. You're trying to understand how you get these birthmarks on an animal with a funny shape. And the shape and size of the animal as it's developing is critical to the distribution of marks on its back. Now, if you imagine that we were little tiny fleas living on the leopard's back, if we were so small, smaller than a flea, we might think that this one spot that we were living on was the whole animal, or that the animal was infinite. We might not know that, in fact, it's a finite animal, but we're just small relative to the variation in its color. And if we're able to, if we're big enough to map out a larger region, we might start to realize, oh no, this animal goes from spots to light, or like a zebra from black to white. And we might only know if we're large enough to see that far. And from the pattern on the animal's back, we could deduce the shape of the animal. And this is similar in the universe. By looking for these hot and cold spots, we're asking, can we deduce the entire shape of the universe? Now, we don't know yet, but there are satellites being launched. There was one launched last year called MAP, and there's a satellite proposed in the next couple of years called Planck Surveyor. And from the details of these satellite observations of this radiation left over from the Big Bang, we think we might be able to reconstruct the shape of space. So, although I should say those satellites aren't launching for that reason. They're launching because they're more interested in the curvature. They're more interested to find out if we live on something like that convex mirror or if we live in a flat universe. But we're piggybacking on those experiments to say, well, we might as well go the whole way and figure out if we can see all the way around the cosmos. These are just, I'm just going to kind of flick through these pictures. These are hypothetical mathematical pictures I generated with a lot of my collaborators. I should say lots of really interesting people have worked on this. You can find their names in my book, because I'll miss somebody and they'll be really mad. You can sort of see that the pattern starts to emerge when I have different, if we lived in some funny shaped space, don't worry about the exact shape of space, the pattern in the hot and cold spots would change as the space changed. And these are sort of encoded patterns that we might see in the shape of space. That's just kind of a little zoo. And we go through, by predicting, we go through mathematically trying to hypothetically reconstruct what the sky might look like if it had these different shapes. But at the end of the day, what we really need to do is look out in the sky. It's like trying to idealize a leopard and then match it up perfectly. We don't really want to do that. We want to go to the zoo and look by eye and say, oh, there's a zebra, there's a leopard, there's an elephant, there's an anteater. So I think getting to the close, it's clear that there's this cosmic zoo of possibilities. The reason why we don't know where we live isn't just because we can't observe it. So we also theoretically don't have a prediction. We don't theoretically have a prediction for the entire shape of space. And it is possible that the theories will come back as we plow along more and more. I don't think I'm using my conclusion page, so I'll just go here. As we plow along more and more, that we'll start to say, well, maybe the universe really is infinite. So people often ask me, why do you believe the universe is finite? And it's not about belief. It's not that I believe one thing or the other thing. It's that there seems something untenable about an infinite universe. And I'll just end with that, I think. If you imagine an infinite universe, it means that there's an infinite number of galaxies in that universe. And there's an infinite number of planets in those infinite number of galaxies. And one of those planets has got to look infinitely close to the Earth. In fact, there's an infinite number of them that look infinitely close to the Earth. And then there's an infinite number of rooms right now, somewhere in space, where we're all having this conversation. And it starts to seem really absurd. Now, it's not actually impossible, but it starts to smell of something rotten. And, maybe we are so arrogant, we'd like to believe we're such individuals that it's not possible, but I actually think it's worse than that. I find it really hard to believe that somewhere else in the cosmos, there's exactly this distribution of people having exactly this conversation. And then somewhere else, there's a room slightly different, where people have made slightly different choices, slightly different mistakes, have slightly different lives playing out. So it hints that maybe we should be thinking differently. And so we take this as a piece in the puzzle. In the meantime, until we have a better theory beyond Einstein's, or until we actually have an observation. Thanks. And I'd like to take questions, so thank you. I'm gonna try to repeat the questions for the so everyone can hear it, but if I forget, just remind me. Question in the front here, and then sorry, next.
In your book, the title of how the universe got its spots, I take it as at least something discussion of how it ceased to be uniform, or something which would have set the ball rolling as far as galaxies and such. Mm-hmm. Is there anything that would either a spherical or a saddle-shaped space time think would affect which kind of spots you've got, or how it would spots, and then can you reason from the spots back to the...
Right. So the question is there some way that the shape of space, whether it was flat or spherical or negatively curved, would it affect these spots? And how would it affect the spots, I guess? And yeah, that's exactly how it did. It would affect the shape and size of these temperature differences. And again, back to the analogy of the leopard, it turns out that if it's finite, just to harp on this point, that because of the geometry of it being like a cylinder, it actually determines the pattern. And if it was more tapered, like the tail, you'll often see stripes drawn out. So it's a matter mathematically of it's formally called solving the Laplacian on a finite space. You're solving a wave equation on a curved space with finite boundary conditions. And it absolutely does affect the shape of space. And if you can think of it as also water waves, you can imagine having water waves in a funny shaped pool or with funny boundaries, and it will certainly affect the pattern of waves. And that's really what these are. These are hot and cold waves running through the whole cosmos. They're not considered to be that independent. They are peaks and valleys in a wave that ran through, in some sense, the space. Okay. Is another question?
If I understand you, that's always a question. You seem to be denying the admittedly unprovable hypothesis of singularities preceding the Big Bang, similar to the hypotheses of singularities within black holes. Is that correct?
So the question is, I seem to be denying the absolute definitive existence of singularities in the Big Bang and also in black holes. So first, just to describe what a singularity is when space-time is curved so intensely, it's actually infinitely curved. And that's what they think happens in the centers of black holes, and that's what happens in the Big Bang. And I don't think anybody really believes in singularities. I think they think it's a mark of Einstein's theory breaking down. So the theory describes these incredible curvatures. So a black hole as being kind of a funnel in space, this incredibly strong curvature, but it goes to the point where it actually allows it to become infinite. And even Einstein wanted to believe nature would protect us from the formation of these infinite regions of curvature, that they were somehow impossible in a valid physical theory. Again, what he was doing was rejecting infinity. So Einstein also said something really funny. He said, only two things are infinite, the universe and human stupidity. And I'm not sure about the former, he said. and neither am I sure about the former. So what we're doing, in the book, I think I said it was like a dead man scratching clues in the dirt. You know, that's what the theory is doing. It's pointing to its own failure. It's saying, I can no longer handle regions of this extreme curvature. I can't tell you the answer, but I'm breaking down. You know, this is where the theory is no longer any good. And as we try to do quantum gravity theories, as we try to make some kind of union between physics on the smaller scales and physics on the larger scales, the aspiration is that those kinds of infinities will go away. That is certainly one of the hopes, which is why also the initial Big Bang will be rewritten, as will the size of the space it creates in those early moments, will be rewritten by a theory that has not yet really come to fruition. It's dabbled at in string theory, dabbled at in quantum gravity theories. Just going to move out in the room. Any other questions? Oh, you did? Well, I keep tapping the mic. Sorry.
Brad, you want to put in a battery? Oh, the red light is really dim.
I should just launch right now.
Do we have a...
The battery went dead? When did you guys lose me? How far back?
No, just a couple minutes.
And I'm not talking to you guys over here.
We just need to switch the battery.
Yeah. You should see how I feel. Shall I try to take a question in the meantime? Or, oh, you've got one right now. Okay.
Yeah, we're
okay.
fast.
Okay.
We're lightning fast.
Question over here? Okay.
Okay, you can ask the question. Go ahead.
Okay.
Oh, yeah, ask a
You
question.
said earlier that an infinitely large universe would imply an infinite amount of matter. And I was wondering, could it be possible to have an infinitely large universe with a finite amount of matter in it and just a lot of space going forever outside?
It's possible, but it's a really, it's not the most attractive solution. So the question was, I seem to imply that an infinite universe implied an infinite amount of matter. And would it be possible to have an infinite universe with a finite amount of matter? It isn't really possible unless I make the universe really not at all very symmetric. And that's actually much harder to do than it is to just make the universe finite in the first place. That is, Mother Nature doesn't care if this math is hard for us. You know? Really, she's going to do what's easiest. You know, water rolls down hills. Even that's a very complicated thing to calculate. It doesn't take a smoother path to make it easier on us. And so, so that's what I mean by it's easier to make a universe. It means that presumably the laws of physics imply it would be a lot easier, take a lot less noodling and fine-tuning and degree of precision to make a universe which was finite, but had matter more or less roughly evenly distributed throughout it. To create a space that's infinite with matter just in the center is very, very awkward. Very, very awkward. In fact, I'm not sure if you could do it at all. Question over here?
Infinite universe with the turtle going off one end and then his other half coming in the other, is what appears to be the edge at a specific point, or is it movable?
That's an interesting question. If you imagine well, first of all, the turtle does not experience an edge at all. And in some of these spaces, you can redraw the shape if you're drawing it around a different center. Okay, the edge is meaningless. It's just a matter of what would you trace out if you tried to map the space, let's say by blowing up a balloon. If you blow up a balloon and you're standing in one location, you might trace out a different shape than if you're standing at another location. And so it really emphasizes the point that this boundary does not exist. Okay. And again, it's kind of like cutting open the earth again in a way, you know. It's not a great analogy, but I'll use it anyway. You know, you might draw the seams differently each time you cut it open. The earth really doesn't have the edge. It doesn't exist. Okay. So, question over here?
I have trouble understanding what the universe is expanding into. Is it expanding into existing space, or is it creating new space as it's enlarging? Where's it going?
Yeah, this is one of those questions. I think, the question was, thanks. The question was, I have trouble imagining what the universe expands into, and where is it going? I think the clue to your question is you said where, and as soon as there's a where, there's space. And if I can point to where it is, that space exists. It might as well be part of the universe. If there really is no space, it's meaningless to ask the question. If I imagine flatland, I'm looking at it from the third dimension, so I'm assuming the third dimension really exists, and that you can point to it, and for some reason the flatlanders just can't point to it, but we know it's there. Now you can imagine the third dimension really doesn't exist. There is no third dimension. There's no us, there's no three-dimensional creatures. It is just those 2D. And that space can expand in the sense that 2 points on it will move further away from each other, and all 2 points on it will continue to move away from each other. It's not expanding into anything. And so that's really what the whole game of space-time is based on. That's why a lot of these visual aids are deceptive, and we have to really rely on the formal mathematics. Some spaces have to be embedded in other larger dimensional spaces, but most do not. The other question that's often asked is what happened before the Big Bang, so I'm going to preempt it, because I always get asked that. And it's a very similar question. The question is, there really was no time, if that model is right, and the universe had a beginning, and that's a big if, then there really was no time. And if you think about time, time is change. It is the clicking of a talk. It is the movement of a hand from one location to another location. If none of those events ever occur, if clocks aren't built, if cells aren't decaying, if a breath isn't exhaled, there is really no meaning to the notion of time. It's not a meaningful question. In instant eternity, you'd have to build a clock to measure the difference. Okay, so let's take another question from, let me just go further out for the sake of it. Back there?
How would you describe a dimension like the diameter of the universe? If the universe it could be conceived of as a spherical shape.
Right, well, so the question is, how would you describe the diameter of the universe? For instance, if the universe had a spherical shape, how would you describe the diameter? I'm not sure what you mean by describe, but usually I think what you mean is what we need in that is a relative scale. We need to know how big is it relative to something. How big is that scale relative to the size of an atom or the size of a galaxy or the distance light has traveled since the Big Bang? And that's how we measure the size of space. Now, we haven't really measured any size to space because so far we can't really be sure if it's curved or not, or if it's infinite or not. We really don't know the answer to that question. If it was at least curved, even if it looked infinite, we'd be able to say, how curved is it relative to the distance light has had to travel since the Big Bang? And we can make some relative comparison between those two things. That's really how we'll be measuring it, relative to the distance light has traveled. Is there a question over here? Oh, over here. Sorry.
Space, say, within a galactic cluster from expanding while space at a larger scale?
The question is, what keeps space from within a cluster of galaxies from expanding while space on a larger scale expands? It turns out that the local gravitational pull of the organized matter is more important than the global gravitational expansion. And it's just a matter of comparing which predominates, which is stronger. There's a Woody Allen joke, I forget what movie it's in, but he doesn't want to do his homework because the universe is expanding. And his mother says, you live in Brooklyn, Brooklyn is not expanding. And that's really the truth of it. Brooklyn is not expanding. On the Earth, what's much more important than the expansion of space is a gravitational pull of the Earth. That's what we're combating every day. We don't even know the universe is expanding until we do some pretty ambitious astronomical experiments. And it really wasn't until recently that we learned that. So that seems to take over on a larger scale when the global clustering of mass is more important on a smaller scale. Back here?
The Big Bang is generally described as an instantaneous kind of event, and I wonder how much truth is there to that. It seems to defy common sense. Everything else in nature is a process.
So the question is that the Big Bang is usually portrayed as an instantaneous event, and how realistic is that since everything else in nature tends to be more of a process? I think that, again, this is because of the limitation of the current working theory. And in fact, some people say that with quantum gravity, we won't have sort of point-like anything. We won't have instants in time or point-like matter. Everything will be sort of relational processes. That is how we will fundamentally understand everything. That we will come to think that there's no actual particles in the universe, that there are just events. And we perceive these events to be organized particles, or on some large scale, they begin to look like that. So when we rewrite the story of the Big Bang, presumably, it's going to be quite different. Although we know pretty well what happens very, very small fraction of a second after the Big Bang. 10 to the minus 35 seconds after the Big Bang, our theories are doing okay. 10 to the minus 30, that's such a small number. But, also people say, well, what does that number mean? Again, to the idea of building a clock. You couldn't possibly build a clock back then. It's really hard to say what that means. Those units are human units. They're units that we use because of the sun and the Earth's rotation and the lunar cycles. This is how we've invented years, minutes, seconds. It's really hard to understand what that scale really means back then. But nonetheless, the point is that we understand pretty early on what it's looking like. Now, before that is a Pandora's box a bit. There was a question. This woman here.
I'm just wondering, has anybody ever considered the amount of decibels that were generated by the Big Bang?
The number of
in terms of sound, has anybody ever determined
decibels.
or tried to determine the amount of decibels?
So the question is, has anyone ever tried to determine the sound or the decibels? From the Big Bang. It's not as crazy as it sounds, actually. The point is that a sound, not to imply it was sounding crazy, a sound is it's a wave in air or water or some medium. Okay, so to make sound, you need to cause oscillations in some medium. Now, the universe, when it's first existing, and these small moments, there hasn't been enough time to create a physical oscillation across matter. In fact, we don't really know what matter looks like in terms of quarks and the plasma. It's a really crazy plasma. However, one of the earlier questions and map, and these experiments look into the sky, what they're trying to measure is acoustic peaks. What they're really measuring is sound waves in the medium of the universe, in the matter of the universe, not in the first instance, but after, say, 300,000 years into the universe's life. And it's these oscillations that are causing, again, little hot and cold spots in this radiation left over from the Big Bang. So the radiation's there and this matter is sloshing, and it causes it to Doppler shift, to heat up a little in one direction and cool down a little in another direction. So in a sense, I suppose you could probably turn that into a sound. I never really thought about it. But. I'm way in the back over here. Yeah, he's got his arm way up, but he's looking behind him.
Is there any mathematical credence to the Big Crunch theory, the idea that at some point the universe will contract?
So the question is there any mathematical credence to the Big Crunch, the idea that one day the universe will contract? Mathematically, yeah, there's certainly perfectly viable solutions to the theories we have available that say the universe is expanding, it will eventually stop expanding and recontract. It's just like throwing a ball up in the air. It will eventually stop and then come crashing back down. And if it does recollapse, it will go back towards what's called a big crunch. It will run the whole movie of the universe backwards. Now what happens thereafter, we don't really know. Would it bounce back out? Would it continue to just oscillate, bouncing, and we'd have history after history where the entire cosmos was erased and started over again? It's a perfectly valid solution. Now, again, these are all pieces in a wider puzzle, and until we've made further theoretical steps, I don't think we have any idea which, we can't say one's right, or I believe in this one. All we can do is say, it's worth pursuing this. It's worth pursuing the possibility that there will be a big crunch and a series of oscillations, and that, in fact, the universe didn't have one Big Bang event. It's infinitely old. It's had an infinite number of Big Bang events in the past, and we're just one incarnation in the true history of the cosmos. And we're just somewhere in the middle of an infinite series. Of course, if it's really infinite, there's no such thing as the middle. You know, you can always slide it around. Let's see. Question over here?
When the Big Crunch would start, would this tell you or not whether the universe is infinite?
Yes, it would, actually. If we could predict, the question was, if you could predict when the Big Crunch would start, would you be able to say something about whether it's infinite or finite? I lied a little bit. There was one solution to Einstein's theory that's completely predicted by Einstein's theory as a possibility that is, in fact, finite. One solution only. And in that model of the universe looks like a three-dimensional sphere. And it is completely finite. And it will have this big crunch. It will expand to some maximum and then recollapse. And so if that's what we find out, then in fact the universe is everywhere positively curved, like a sphere. It's a three-dimensional sphere. Then we should be able to predict when the big crunch would happen, and we should be able to tell the size of the space indirectly. Now, I should also say that most people believe that we live on such a small patch. It's like living on the Earth and not realizing it's curved, and we don't realize it's curved because we live on such a small patch. If we were standing on a basketball, we would know it was curved, right? It's because the Earth is so huge relative to the human scale that we think that people made the mistake of thinking it was flat. So similarly, you wonder how small a patch do we occupy in a finite universe? And that's why a lot of people, and I might include myself in this, believe that even if the universe is actually finite, and that's theoretically a better way for the universe to initiate, we might never see it. And so it's really a matter of doing quantum gravity and looking at the small secrets in terms of trying to get the big picture. So even when people say, for instance, that the universe is flat, they don't really mean that it's flat. They just mean we live in such a small local patch that it looks effectively flat. And they're not willing to say what's beyond that. Way in the back over there.
I got this straight. So your spots are actually an image taken by the Colby telescope, or the Colby satellite, of the universe at 300,000 years after the Big Bang, correct?
That's right.
And then the spots represent temperature and density variations?
That's right.
And that they're the seeds of what the galaxies are today?
Well, I didn't say that, so you've been studying that.
Okay, well, I wasn't sure, but okay. Now, one last thing is, when they took the photograph, are they taking the photograph of the temperature at like 3 degrees above absolute zero?
Yeah, the temperature today, I said it's very, very, the universe was once incredibly, unfathomably hot, and it's been expanding for so many billions of years that it's actually quite cold now. It's 3 degrees above absolute zero is the temperature that they're looking at. That there is this cool echo everywhere, this one temperature, and these tiny hot and cold spots are very, very, very tiny variations above that temperature. They're 1 part in 100,000 different from the average. It's very small. That's why these experiments are so sophisticated. So just, I forgot to repeat the question, but you get the gist. Now, what was the question was? The question was just reiterating that the COBE experiment looked at the radiation that was left over from the Big Bang. It's looking at it at an age of 300,000 years into the universe's life. These little colored spots are slight hot and cold spots about that average temperature, and they're caused by variations in curves in space and variations in density. And the point that was added on was that these variations in density and curves in space ultimately seed galaxy formation, and that's also believed to be quite true, that there's no way, the universe is created with lots of matter whizzing around everywhere, and somehow it organizes in clumps into galaxies and clusters of galaxies, and very, very fascinatingly ordered structures. Did we just lose this again? Yeah, I heard it go off that time. Sorry. How are we for time, anyway? Okay. So those little variations also form the structures of galaxies. Is it still on? How did I lose it?
Oh, it's you? Okay.
Oh, it's... What'd you do? Oh, there you are. Okay. Question back here?
Yeah, what about your personal preference? Is the universe flat or curved? Is it infinite or finite?
Mm-hmm. So the question was, what's my personal preference? Is the universe flat and curved or infinite or finite? And, all universes are created equal in my mind. It's, the Orwell story, Animal Farm, but some universes are more equal than others. I think that a finite universe is a much more elegant way for the universe to explain itself in a way. It's not that I don't believe it one way or the other. If the data comes back, if the theories come back and convince me otherwise, I will be happy to abandon that notion. But I think a lot of times what you're doing is saying, this doesn't sound right. It's worth taking that step. It's worth pursuing the possibility that, in fact, the universe is finite. Now, I do think that if gravity, if space-time is really to be unified with the theory of physics on the small scales, then gravity, space-time, all these things are really just different expressions of matter. I know it's hard to believe, but they're really like different phases of water. Ice and steam are ultimately really the same thing. They look totally different, but they're both H2O. And the idea is similarly that gravity is really the same thing as matter. It just looks really different. It's a different phase of matter. And if that's true, I would like it to be born finite. I think that would be a more elegant story. And also, when you look at things like string theories and theories of quantum gravity that try to go beyond Einstein's theory, it's very natural to talk about finite spaces. Astronomers thought this work was incredibly esoteric, but particle physicists didn't bat an eye. Absolute everyday occurrence for them to talk about 10 extra dimensions that were topologically compact and rolled in on themselves and had funny shapes. And so it really depends which community you're in, how heretical it seems. Back there? Question in the very back?
Expanding into.
Oh, that got asked already. The question was, what was the universe expanding into? Which I think we already addressed. Does anyone want to see if they studied well? I want to hear. It's a test. It's a quiz. So the answer is really that it's not expanding into anything, that it's just space itself. It's the end of the story. We can't go through it again. Here in the middle?
Yeah. A couple of quick questions. One of them, I thought you were going to explain why there is such a pattern that COBE discovered and why it's not uniform, this background radiation. Mm-hmm. And I'd appreciate it if you can kind of elaborate on that a little bit. Okay. And the second one, can you tell already from as rough an image COBE has provided that there is none of the type of symmetries that you're looking for?
From COBE?
From COBE.
Mm-hmm. So the question was, could I say something about the pattern that COBE already observed, why it isn't completely uniform? So COBE was that experiment that was launched over 10 years ago, which I first showed up with the hot and cold spots. And can we use COBE to look for the shape of space? So to answer the first question, the pattern actually looks pretty uniform. There are hot and cold spots, but they seem to be very, very, very evenly distributed throughout the cosmos. This is one of the great mysteries, actually. What it seems to say is the temperature of the universe is this 2.73 degrees above absolute zero. But it's like that in every single direction in the sky. And the only variation are these 1 part in 100,000, slightly hotter, slightly colder. Now, if you were an archaeologist and you found evidence that there were ancient civilizations that you thought lived at opposite poles but were speaking the same language, 1 part in 100,000, you wouldn't think this was a coincidence, right? You would think they must once have been communicating. They must have shared a language and come to understand each other. And similarly, by looking at this and finding that, in fact, the sky is so similar across a vast expanse of what looks like nearly 30 billion light years, that space must have once been in causal contact. They must have averaged out, like the temperature of this room comes to some kind of average. And the theory which tries to explain that is called inflation. It's a very important paradigm for how we understand how it could be possible to start with a universe which is very small and is now so vast, so huge, and so smooth. And this is one of the important theories we're testing with the future satellites. Now, the question about whether or not we can measure the shape of space, we can, but not well enough. For instance, you can ask, what if the universe was really this funny parallelepiped, this funny square, cube, rather? Could it match the COBE data? And it turns out it can. You try to fit this radiation in this small square. You try to generate the pattern that would emerge by, again, jamming this balloon, if you like, in this small box. And it is consistent with COBE. It says that if that's the case, the universe is maybe around half the size of the observable, maybe 15 billion light years across as opposed to 30 billion light years across. But it's not proof of. It's simply a consistency. So there's been a lot of work on that. Question here?
Yes, when you talk about the Big Bang as singularity, and also you mentioned singularity with black holes. Okay, you have the Big Bang, which would be a very massive black hole, I assume. Why haven't we observed any little bangs?
The Big Bang isn't exactly a massive black hole. They are different. Their singularities might be kind of structurally different, but they are different. Black holes don't emit anything. They don't emit light. They don't reflect light. That's why they're black. They're dark. If there's a black hole out in the... Sorry?
Don't think it's so often.
Evaporate? So Stephen Hawking is most famous for his suggestion that black holes will in fact evaporate. And the reason why it was such an incredibly important idea was because it seemed theoretically impossible. All black holes were defined on the basis of the fact that they absorbed matter and did never let it go again. Never emitted matter. So what Stephen Hawking did is he combined that theory with a theory of particle physics. So he combined two different theories of physics to come to the understanding that, in fact, if I looked at the quantum level of what was going on around the black hole, I might find that black holes evaporated, that they emitted light, or particles rather, and slowly evaporated. It's slower than the age of the universe for most black holes. It's not a realistic process. It was just formally a very, very important process. Certainly not a way to observe black holes, and it's not going to make them go away. And I forgot to repeat that question. I'm really sorry. I just want to get distribution around the room. This question here? I'm not skipping anywhere. I'll come back to you, I promise.
I think the Big Bang was not a black hole. You didn't finish that.
All right, so the question, well, now I'll repeat the question. The question was, if the Big Bang is similar to a black hole, they're both singularities, why don't we see any little bangs around space? And that's because they are different. So the black hole, it's not that the black hole on the inside might be looking like a Big Bang. In other words, if you fell through a black hole, you would never see this universe again. You would never see this outside world again. You would fall into the black hole, but you might come out in a kind of Big Bang event somewhere else. So there have been models where they try to imagine sewing on the center of a black hole to a Big Bang event, but we can't see it because it's hidden behind this dark exterior. It like balloons out somewhere else. And again, this is just an idea. There's no way it's been proven, and it might never be proven, but it's just something that people have played with. A question in the back there?
Yes, I was wondering what you think the latest idea of this dark energy or quintessence is, and will the MAP probe or the Planck Explorer help us determine what that quintessence or dark energy actually is?
So the question was a question about the dark energy, otherwise sometimes known as quintessence. Quintessence is a specific theory about the dark energy. and whether I think MAP and Planck Surveyor, these future satellites, will resolve that. So the answer to the last part is yes, MAP and Planck Surveyor will hopefully tell us at least whether or not the universe is accelerating. Now, the dark energy is this very mysterious thing. What happens is that we look out into space and we see that not only is the universe expanding, it's actually getting faster and faster and faster. And this is done by looking at supernovae that have exploded, stars that have died and exploded very, very far away, that by studying the pattern of how they heat and cool and the temperatures of these supernovae, we can figure out how far away they are and how fast they're moving away from us. And it looks to us like the universe is getting faster and faster and faster. It's a very unexpected turn of events. Nobody would have said that, I think, 5 years ago or 10 years ago. And the only way we know how to drive that expansion is with something called dark energy. And the reason why it's called dark is because we've never seen it. People have probably heard of dark matter. And it's also because we've never seen it. It seems to be that the curvature of space, the expansion of space, is pointing to a universe where over 90% of the constituents are things we have never heard of or seen before. So whenever you hear this statement, oh, cosmology is solved, it is the opposite. It is just the beginning. We're going to have some numbers. We're going to know how fast it's expanding, what the curvature is with these future satellites, but we're still going to have no idea what's out there. And we seem to be this sort of dusty sediment, a very, very small fraction of what's out there, not at all common, if this turns out to be correct. And so the big push is going to be for particle physicists and cosmologists to come together to understand what fundamental matter and energy could be so novel and so weird. And then there's a question here, which I promised I would take. You can't believe I finally picked you.
For my question. Will curve space appreciably and light following it in the small distance like the 93 million miles between the Earth and the Sun? I say that because I've noticed at the time of the half moon, if you draw a line from the top and the bottom of the terminator and draw a 90 degree to that, it doesn't, here's the sun on the horizon, that line doesn't point to the sun, it points above it. And I wonder if light could curve in that small space.
Well, I'm going to answer it slightly differently. So the question was, in the distance between the sun and the Earth, is the mass basically of the objects in our solar system strong? Is the mass of the objects in our solar system strong enough to curve space in any measurable way? That's another way of asking the question.
To give that effect, yeah.
Yeah. Well, the only effect well, there's only a couple that I know of. I don't think it's strong enough to do anything like that. But the curve is strong enough to cause light to bend. So if you look at a star behind the sun, it will make a very, very, very small deflection in its path to the Earth. It won't just cut straight through. And if you think about how you would observe this, it's incredibly difficult because the sun is blindingly bright. How are you going to follow a little tiny squirt of light from a distant star? And the only reason we can do it is because there's a total eclipse. And it just happens coincidentally that the moon subtends the right size in the sky to completely occult all the light from the sun and allow this sliver of light from a distant star to pass through. And when this experiment was first performed, Einstein was congratulated and his theory finally been proven. And I don't really know what his remark was. It was something to the effect of, well, what'd you expect? He seemed pretty confident. And there is also something about the precession of Mercury. It has to do with Mercury's spin, where you can see the curvature effects. That Mercury's spin seems to precess a bit, and it's a purely relativistic effect.
That might explain this paradoxical thing I see.
I don't think so. I think that's. I'm not sure. I'm not so good in the planetary stuff, but I really don't think the scales are just right.
Next half moon, look at the sky.
All right. I never look at the sky. What's the question back here?
The final argument against an infinite universe, which is that even if there are an infinite number of galaxies, it would still only be countable. And there just isn't room in a countable infinity of galaxies to repeat this room.
You're saying if the universe was infinite, we would be able to count an infinite number of galaxies? Was that the question?
Yes.
Well, the reason, there's two parts to it. First of all, we've only been around for a short time. And if I tried to count an infinite number of pennies, I would only get to a finite number in the history of my lifetime. And similarly, these galaxies have only been around for a finite time. And so only the ones close enough for the light to reach us are countable at all, let alone our own limitation.
I was which isn't countable in the technical sense. That's a classification.
You mean the number theory countable?
Yes.
Oh, are you asking me if they're countable in the number theory sense?
I'm asserting that they're countable.
Not necessarily. I'm not 100% sure about that because some of these spaces, so countable infinity has to do with infinity itself is a weird idea. You know, Cantor was this great genius mathematician. He spent his late years in a mental asylum, needless to say. And he was the first one to really push the idea of infinity. A lot of people before him did not believe infinity had any place even in mathematics, let alone in reality. And what he proved is not only are there infinities, for instance, the natural numbers 1, 2, 3, 4, 5, up to an infinite number, but some infinities are bigger than others, you know. And that's where he got really clever. And one of the smallest infinity, I think, is the countable infinity. It's related to the size of the natural numbers, 1, 2, 3, 4, 5. It can be put into 1, 1 alignment with those numbers. It's not the biggest infinity imaginable. There could be a bigger infinity. And I'm not 100% sure, depending on the shape of space, if it's countable. I'm not 100% sure it's not, but I wouldn't leap to the conclusion that it's countable. If you look at a negatively curved space, you can see that there is a certain proliferation of size, in a sense, as you get further and further away. A lot of these spaces have, for instance, chaotic properties and peculiar things which are related to exponential growth of possibilities. It's not 100% obvious to me that it's countable. I think I stumped you out of asking me more of that question. Question over here.
Why does it seem necessary in string theory to have 10 or 11 dimensions instead of 3?
So the question is, why in string theory is it necessary for there to be 10 or 11 dimensions instead of 3? There are some string theories, I think now, which are strictly 3-dimensional with the extra dimension of time, 3 plus 1. 3 plus 1 dimensional. Originally, it had to do with curing odd behavior in the theory. It was perfect. It was a purely mathematical and formal glitch. That if they didn't do that, they wouldn't get, they had to what's called renormalize, actually it was an anomaly thing. I think it had to do with the anomalies. So it was in order to get certain glitches out of the theory, it just happened that if you made it in extra dimensions, it works. Now the reason why that's intuitively at least plausible is because in string theory, the suggestion is that matter is not fundamentally a point particle. If I looked close enough at matter, I would see that it's actually individual strings. And that each atom, each particle is really a different mode or vibrational mode on this one fundamental type of string. And if you imagine a string and the modes a string can have, the different ways it can make a note, if you like, then the number of dimensions it can wiggle into is important and can change that spectrum. Or it can change the songs it can play, in a way. So that intuitively you can imagine that the certain shape and size of the extra dimensions will create different distributions of particles in the universe, and will therefore be required to make it look like the universe we live in, with the matter we live in. You can let me do this all night. No, I don't mind. I can do this all night. How many more questions do you think? One more question? Okay, in the corner there. There's a question in the corner. Yep.
The main problem seems to be combining like quantum theory with relativity. I mean, do you see some kind of new math breakthrough that might do this, or?
Yeah. So the question is, a lot of the areas that I'm interested in, I'm always saying things like, well, we don't really know yet. It's just a piece of a puzzle. And the reason is it's the combination of Einstein's theory of relativity with quantum theory, and that has never been smoothly sewn together. And the question was, do I foresee a new branch of mathematics that's going to clear this up? Was that the question? Or a new leap? Well, there's another book by Lee Smolin called 3 Roads to Quantum Gravity, where he talks about the 3 tracks that people are taking to really make leaps. One of them is string theory. One of them is pure quantum gravity or canonical quantum gravity. And another one I think was just classified as other. I can't remember what the other one was. But maybe more philosophical, looking into the fundamental philosophies of quantum theory and overthrowing that. I personally, don't know. When I've been interested in working on this, I've been interested in doing stuff that is, I think, fundamentally more of a different direction. So people are still looking for a reductionist theory that is one theory of everything. And if you write down this one mathematical sentence, you will be able to calculate, under the idea that nature takes the path of least resistance, all of the laws of physics, everything about the Big Bang, down all the way through to biology, if you could. And we might not be smart enough to do that, but it's theoretically possible. So I've been wondering, what if there isn't such one fundamental sentence, but many competing sentences, if you like? And the universe isn't ultimately reductionist, but you had complexity at the core instead of reductionism at the core. Something more like complexity or chaos theory at the core. I haven't made much progress, but I've just started.
Before we thank our speaker, just two notes. This morning, the art director of Skeptic, Pat Lindsay, pointed out that it's 10 years exactly that we started this thing, and we brought The Amazing Randy out in 1992 and started work on Skeptic magazine. So I guess today's our 10th anniversary. I almost forgot. And second point, we don't have many celebrities in Skeptics, but our own Julia Sweeney from Saturday Night Live is here today. Not embarrassed, Julia. Some of you saw her and God Said Ha monologue on Oxygen recently. It's been running. She did her God monologue here for us, which is now being called... What?
My Beautiful Loss of Faith story.
Her Beautiful Loss of Faith story, which is going to New York this next month, right? So congratulations to you and taking that to you. We have just 4 copies of Jana's book left. Of course, you can pick it up at Barnes & Noble and Amazon.com, the local bookstores, and so on. Thank you very much.
Thank you. Thanks. I actually have we have...
Jana Levin is an advanced fellow in applied mathematics and theoretical physics at Cambridge University. How the Universe Got Its Spots, Diary of a Finite Time and a Finite Space, is published by Princeton University Press, on the web at pup.princeton.edu.